So hello students, today we will be concluding the unit capacitors, and today whatever I am going to discuss is mainly conceptual, and it will help you in solving the numericals of a higher standard. Now in the last lecture we had discussed that when a dielectric is placed in an external field, it gets polarized and induced charges appear on it. So today we are going to find what is the magnitude of this induced charge. Now I have taken the same parallel plate capacitor, the plate cross section area as A, and Q is the charge on the plates, and electric field E, this is the electric field in absence of dielectric. And again we have placed a dielectric. Imagine that you have placed a dielectric in between the plates. Induced charges appear, say QP. Let me represent the induced charge as QP. And the electric field due to polarization as EP. And we know that the field within the dielectric, which we express as EM, will be the external field minus the electric field due to polarization. These things we had discussed in the last lectures. So this is the field in the medium, E minus EP, it is the field in the dielectric, and QP is the induced charge due to polarization. Now since we have expressed the electric field as sigma by epsilon naught, this is the electric field between the plates in absence of any dielectric, that is only in presence of air or vacuum. And this we had arrived at this result using Gauss's theorem. So we can express the electric field due to polarization, that is within the dielectric, as the surface charge density of the induced charges by epsilon naught. And the field within the dielectric will be the difference of E and EP. So it is expressed as E minus sigma p by epsilon naught. And I have substituted for E, and I have solved it. I have substituted, I have solved here, and we know by definition that the electric field in vacuum to the electric field in medium is equal to the dielectric constant K. So we have replaced the electric field in the medium by E by K here, and so we have expressed here EM as 1 by A epsilon naught Q minus QP. I have substituted for EM, and then it is equal to what? It is equal to E by K. So I have substituted for E, which is Q by A epsilon naught into 1 by K. And then on solving, we find that the induced charge QP is equal to Q into 1 minus 1 by K. So the induced charge in the dielectric is different from the charge on the plates of the capacitor. This is going to help you when you solve the numericals of the capacitor. Now some other alternative form of Gauss's theorem is also to be discussed. Here we have again taken the parallel plate capacitor carrying a charge plus Q and minus Q, and we have placed a dielectric over here. The induced charges are shown, it's minus QP and plus QP, and we are going to find the electric field in the dielectric using Gauss's theorem. So I have drawn a Gaussian surface PQRS, and we apply the Gauss theorem. So now since we are going to find the electric field in the medium, so I have written as surface integral of electric field in the medium, and I have taken the dot product with the area vector, that is EM dot ds, should be equal to charge enclosed upon epsilon naught, that is Q minus QP by epsilon naught. And just in the previous derivation we have written Q minus QP is equal to Q by K. So I have replaced Q minus QP by Q by K, and epsilon naught is still there. So we have an expression K EM dot ds is equal to Q by epsilon naught. This is one form of Gauss theorem. This is the form of Gauss theorem in presence of dielectric. It's the same thing as we had expressed that E dot ds is equal to Q by epsilon naught, because here it is EM and we have used the constant K also. So it's the same thing, but in a different way. And there is another form of Gauss's theorem also, Now we had learned that the electric field due to polarization is equal to sigma p by epsilon naught, and in the previous lecture we had seen that the charge density due to polarization is equal to the magnitude of the polarization vector. So we can write EP as sigma p by epsilon naught, which is same as p by epsilon naught. And also the field within the medium is the vector sum of the external field and the electric field due to polarization. So electric field due to polarization opposes this field. We have already seen these things. So I have substituted for EP as p by epsilon naught, and since it opposes, I have put up a negative sign over here. And look, we have taken the LCM and we arrive at an expression epsilon naught EM plus P is equal to epsilon naught into E. And this epsilon naught EM plus P, I have taken the dot product of the area vector on both the sides, dot ds, and here also dot ds, and then I have integrated over both the expressions on either side. And in the one of the last lectures we had seen that epsilon naught EM plus P, the vector addition of these two, is nothing but the electric displacement vector D. So I have replaced it by D, and D dot ds is equal to epsilon naught E dot ds, and we know that E dot ds is equal to Q by epsilon naught. This was Gauss theorem. So we arrive at the expression D dot ds is equal to Q. D is the displacement vector. If there is no polarization, then it's obvious that this vector will be equal to 0, and displacement vector would be only epsilon naught into EM. So this is again another form of Gauss's theorem in terms of displacement vector. So in absence of polarization, we can write the displacement vector as epsilon naught into EM, or you can replace it by epsilon naught E, because if there is no polarization, that means the field, there is no medium, so the field in the medium is same as the field between the plates of the capacitor. And if dielectric is present, then we can replace this E by K into EM. So the displacement vector is epsilon naught into K into EM, because we know that the ratio of E and EM is K. So this is all we had to do in capacitors, and now you can practice the conceptual questions, you can do the numericals, and in the next lecture we will be dealing with the next topic. Thank you.